All right, hello everyone. Sorry, my microphone wasn't being recognized for some reason or another, but that should all be working now. Let's get up some relevant information here. Hello everyone. Hope you had a good weekend. Welcome to week 2 already here. So hello to Hannibal, hello to Abu, hello to Tolu Walana, hello Emmanuel, hello Alka, hello Yanis, hello Emmanuel, hello Munene, I hope I'm saying that, or I see Dennis. What questions do you all have for me today? We can work some more on the IP mini project, or if you have other questions for me, things you want to discuss, I'm happy to do so. Hello Sarfaraz. Hello Tolu Lope. I hope I'm saying your names correctly. Hello Syed. Hello Abu. Let's see here. Let me open up my IP mini project. Let me run my code up to this point. So question 1, question 2, Lucas Lamer, question 3. I never quite got to doing my version of question 3, which we shall, I guess, need to do so. Let's run everything above. So we've talked about Mersenne numbers, right? Mersenne numbers 2 to the power p minus 1 for some number p, not necessarily prime, but Mersenne numbers can only be prime if their exponent p is a prime. Remember, not every Mersenne number is a prime number, even if the exponent is a prime number. They're only candidates. Thursday last week, right, went through exercise 2, the so-called Lucas-Lamer tests, which we're not going to go into the mathematical details, right, but this is, as it says, given a Mersenne number with exponent p, we define the sequence in this fashion, and then I see, yes, exercise 3, I remember now, right. This is a way of checking if a particular Mersenne number is in fact a prime number. Right? For a given Mersenne number with exponent p, the number is prime if the Lucas-Lamer series is 0 at position p minus 2. So this, yes, I could talk about the zip function. Right, so this Lucas-Lamer series, it begins with 4, and then we have 4 squared minus 2, will be 14 mod this Mersenne number, and then say it's 14, well then 14 squared is what, 196 minus 2 is 194, mod this number, etc. Right, and the idea is, it says the Lucas-Lamer sequence up to and including I is p minus 2. And basically the idea, like, this is the series for this exponent of 17. Essentially the idea is, well, if this sequence ends in 0, if this sequence ends in 0, then the corresponding Mersenne number, so 2 to the power 17 minus 1, is a prime number. And that's what we're trying to do in question 3, right? We want to, we know how to compute this. We know how to compute this Lucas-Lehmer series. And if we put in, so if we have an exponent p, we could compute the Lucas-Lehmer series. This is what Lucas-Lehmer p is doing. And we look at the last term in the series. If that's 0, then we have a prime number. And to denote a prime number, we're going to return 1, or true. Right? We're basically returning true and false, or in this case, we're told to return 1 and 0. So so let me redefine this function. So Lucas-Lehmer prime 5 returns 1, so 2 to the power 5 is 32, minus 1 is 31, yeah, 31 is a prime number. So we return 1. 7, oops, not 75, 7, that's 2 to the power 7 minus 1, 2 to the 7 is, what, 2 to the 5th is 32, so 64, 128, 127, 127 is a prime number, yes. If we try 11, yeah, 2 to the power 11 is 2048, minus 1 is 2047, it's not a prime number. So, what we want to do, so first let me talk a little bit about the zip function. Where's a new notebook? The zip function. It could be a useful function. Zip. Zip. A zip object yielding tuples until an input is exhausted. So zip on this set of characters and range of 3 and range of 4, I get 3 tuples. So it said the zip object yields n-length tuples where n is the number of iterables passed as positional arguments to zip. The ith element in every tuple comes from the ith iterable argument to zip. This continues until the shortest argument is exhausted. So what does this mean? So I could say, well, let's zip 1, 2, and 3. And let's put the list 4, 5, and 6. Oops, 4, 5, and 6. This is implemented as what's referred to as a Python generator. So, for example, I don't actually see the output, but I could put this inside a for loop. Copy and paste. Print x. And you'll see what I get as output. People are saying the stream stopped. I'm still here as far as I'm aware. Let me double check. Yeah, I could make my notebook a bit larger if that will help. Right, what does zip do? Well, as it says, we get tuples. I get the first element from the first list and paired with the first element of the second list. Then I get the second element of the first list paired with the second element of the second list. And then the third element paired with the third element of the second list. Right, so zip, as we said, we think of, well, I'll line up like these two lists, say, as columns, right? I have 1, 2, 3, and then 4, 5, 6, and I pair up these elements in this iterable. If I had a third list, say 7, 8, and 9, I get tuples. I take the first one from the first list, the first one from the second list, the first one from the third list, and I get tuples. And then I get the second one from list 1, the second one from list 2, the second one from list 3. These don't have to be lists. They could A, B, and C. I have, these can be any iterables. I could stick on a range, 12 to 20, right? And we stop. It goes to the length of the shortest iterable. And so this is what we could use. Well, right, so what do I have? I have, what do I have? I have, let me remind myself, we have our list of Mersenne numbers right here. We have our list of the prime numbers that we want. So what did we want to do? We want to produce a pair of tuples. I have a Mersenne exponent and a 0 or 1. So let's see here. I have the primes I want is this list. What I want to do is, if I create a list comprehension, I say LL prime, I want to check for each of these prime numbers, is the corresponding Mersenne number itself a prime number? For I in primes I want. Right, for the exponent 3, is the corresponding Mersenne number a prime number or not? Well, this is where we use this Lucas-Lehmer test. Right, we check, is the last element in this Lucas-Lehmer list equal to 0? If it is, it's a prime number. If it's not, then it's not a prime number. So I could check all of these things by iterating over the list of primes and performing this Lucas-Lehmer test. Now, this is one list that I want, and this is the other list that I want, and I want to put these together as tuples. So if I do zip on primes I want, and this list right here, well, again, this is a generator, so, well, I could turn this into a list, and I have this list, right? For the exponent 3, the resulting Mersenne number is prime. For the Mersenne exponent 5, well, that's a prime number. For 7, it is a prime number. For 11, it's not a prime number. Right, this is the list of tuples that we want to pass to the grader. And so I could replace this. Let me comment this out right here. Mersenne primes is this thing here. Let me split this cell, right? I could execute this code. Oops. Mersenne primes. And well, it's the same list that the list of tuples that we've created before. Right, and this is what we wanted, right? Your final answer should be a list of tuples consisting of, tuples of this form. I have an exponent. So for 3, 5, 7, 11, 13, 17, etc. And a 0 or 1 if the corresponding number is not a prime or if it is a prime. And I could pass, so we made our list of tuples. I could pass this to the grader, and well, that's the right answer. So yeah, Sabin, if you have your access to your Jupyter pod, this is the same thing you could do in Unit 1 or Unit 2. If you go to Video Links, if you have access to your Jupyter pod, if you go to Video Links and scroll down, it's the same link. And as Giannis points out, it's the same link that you use to get here to this office hour. And the office hours that are showing right here, they should be showing in your local time zone. Right, Monday, this is for Unit 1, this is 4 p.m., that's my local time zone. But this time should be shown in your local time zone. So if you have access to your Jupyter pod, check the schedule there. If you don't have access to your Jupyter pod, you're going to have to send an email to, to the dsmodule@wqu.org to get access. So is there any question on what I did here on exercise 3? Right, it's it's putting these pieces together that we've created before, right? We know how to create the Mersenne numbers for a given exponent. This Lucas-Lehmer test, which seems slightly magical at the moment because I can't remember the details, right? But as it says, well, we generate the sequence of numbers, and this last number that we generate will tell us whether this is a prime number or not. Kwame, you will have access to this video, so once again, to repeat myself, if you go to, there's 2 ways that this video will be available. One is if you go to Video Links on your Jupyter pod, so under Video Links, scroll to the bottom and you see something that says Office Hours Playlist. And if you open this up, you will have a playlist in YouTube that has all the office hours on it, including this one that's going on live right now. So you can access the playlist and you get the office hours towards the end of the week, and only towards the end of the week. If you go to Video Downloads and look under Office Hour Videos, the office hours will be uploaded here as well, but only, basically I've been doing that, I plan to do that likely once a week. at the end of the week. Ibrahim, how do you have access to Unit 2? Have you applied to Unit 2? If you haven't applied to Unit 2, well, that's why you don't have access to it. If you've applied and were accepted to Unit 2, again, well, contact the appropriate email address to get access to your Jupyter pod if you don't have that access already. This is assuming you've passed Unit 1. So, all right, I mean, building up to the, when do you need to apply for Unit 2? You could apply for Unit 2 right now if you want to get access to the next iteration of Unit 2. You know, you're going to have to pass Unit 1. No, you don't have to wait for the Unit 1 results. You could apply right now. But, you know, admissions are done to Unit 2 after the deadline for finishing up mini projects. So the mini project deadline, of course, to finish everything for Unit 1 is Friday, June the 18th. But you can apply for Unit 2 now. Admissions for Unit 2 are only done after this mini project deadline has passed. So you're going to need to pass Unit 1 in order to get into Unit 2, but you could apply now for Unit 2. So this exercise, yeah, you might have noticed the primality check we developed is slow for large numbers. I think one or two of you have noted that on this site, right? This takes a long time to calculate. And yes, if you use the isPrime function as written, this is going to be slow. How to apply for Unit 2? Well, it's this same link where you applied to Unit 1, I believe. Or, you know, it's essentially the same process you went through to apply to Unit 1. I don't have that link on hand. But yes, some of you've noticed, yeah, the isPrime function takes a long time, the way it's written. Well, we could speed things up. And we'd want to speed things up if we wanted to check, you know, larger numbers. Oh, apologies. Yeah, the current title I forgot to change. I could probably change that right now on the fly. Office hours 5. Today is the 19th. Is that better? I hope. It is office hours 5. Apologies, I forgot to edit the title. So yeah, we could make the isPrime function quicker. So there's suggestions right here, right? The first optimization takes advantage of the fact that 2 is the only even prime number. Right, so we could check, is it an even number which is greater than 2, then we know it's not a prime number. And we could even, you know, do more. We could say, well, is this a is this an odd number? Is it divisible by 3 and is larger than 3? Well, we also know then it's not a prime number. But that could come a bit later. Right? Our second optimization takes advantage of the fact when checking factors of a number, you only need to check odd factors up to the square root of the number. And we could check this. Syed, you did not submit mini project 1. What to do now? Submit mini project 1 when you have a chance. There's no strict deadlines for the mini projects. Just the only deadline is this deadline of the 18th of June. Right? Just submit the mini projects when you can. But if we only need to check factors up to the square root, because if the number's not prime, and if for example we could write n as the product of two numbers, neither of which is prime, neither of which is 1, well, one of them will be, say, less than or equal to the square root of n. So we only need to check up through the square root of n. So we could speed up our is prime and write a new function. Like, for example, we could say if number is less than or equal to 1, let's return false. If number equals 2, return true. How is the grading done? The grading is done, Syed, by submitting to the grader function right here. This is how the grading is done. The mini projects, so the IP mini project that I'm doing at the moment can be found in Data Course, Python, and mini projects, and here you'll find 3 of the 5 mini projects. The other 2 mini projects are under Data Course, Data Wrangling, and mini projects. You'll find again, it's the exact same mini projects as in the other folder, but you'll find the other 2 mini projects here. So, back to my is prime fast. I'll check, is this number less than or equal to 1 or return false? It's not a prime. If it's equal to 2, we return true, yes, as suggestion. If number mod 2 is 0, let's return false. I've taken care now of all the even numbers. What do I do now? We're kind of working up to question 5, Hannibal. What do I do here now? Well, now I want to check. I could check. I could say for let's use the word factor in range of 3. I need to go up to Well, I could go up to number, but I could do it quicker, Giannis. Right? I only have to go up to the square root. Math dot square root of number plus 1, because I need to include the square root. And I could go by 2's. If number modulo factor is 0, return false. If I get through this for loop and I haven't returned false by that point, I have a prime number, so I'm going to return true. Let's check this, right? Rerun the following cell to make sure it finds the same primes as the original function. Someone asked earlier, how do you debug and assert? Well, right, the assert is trying to say, in this case, well, is this number here, or this result, equal to this number? These are returning true-false values. Is this true-false value equal to this true-false value for every n in this range? If it's not, well, then something has gone wrong. You have to determine where they differ or how they differ. Right? An assert is, in this case here, is just saying, well, is this equal to this? If they're not, you have to figure out where it went wrong. You might add in something. You might do a print, right? Print n, or you could add in a try except block. Try this. If there is an assertion error, print out the value of n. Right, but that's all assert is doing. I mean, literally it's saying, is this equal to that? And is this true for every value in this range? So a couple of questions again. The live stream is recorded. You could find the recordings linked from your Jupyter pod. How do you run the grader? Well, you have to make certain that you import this library. Right? You import the grader. This is our grader that we have written. And then you basically run like the cells that say grader dot, like this one, grader dot score dot and a question name, right? And you need to give the proper input. Check the in mini project, right? The grader is described a bit more in the first mini project than the in mini project. There are times when you might just give a list. In this case, we just gave a list of numbers. There are other situations where you might write a function. This is what you have to do in the second question of the in mini project. You have to write a function. And the function that you write in that case needs to be able to accept a list of an arbitrary size. Don't just consider the single example that we wrote. That function needs to be able to accept a list of any size and return the appropriate result from your function. So back to, right, we could check, we could say, we could use this time it procedure and we could say, well, how much of a speed up have we gotten, for example? This slow is prime function, you know, well, will take a certain amount of time. The fast version, well, we should get a pretty significant speed up. Gladys, the exercises are not the same as the mini projects. The exercises are things you can try out, you know, to learn something new, try something out, but the exercises are not part of the requirements to pass this course. So this on average takes 6.76 seconds, and about 6 3/4 of a second. This takes 371 microseconds. Yeah, well, we shall get to the VC mini project likely later in the week here. We have time. So, right, we have a significant speed up here. You know, we went from 6.6 3/4 of a second to test this function. And here we, what, the microsecond is what, 10 to the minus 6, I think. Gladys, the exercises are going to be distributed throughout the lecture notebooks. Why did we choose what? We chose this range right here. Why? Well, it's this explanation here. Right? Suppose a number is not a prime number. So suppose I could write a number n as a times b for where neither a nor b are equal to 1 or 0 or n. Right? If n is not a prime number, then I could write it as a product of two numbers, neither of which is 1 or n. And we note that, well, one of these numbers, a and b, right? One of these numbers, a and b, has to be less than or equal to the square root of n. And so I only have to check, you know, I only have to check for factors up to the square root of n if I'm checking for prime numbers. Right, I don't have to check every number from, you know, say 3 up to the square root of n. Or sorry, I don't have to check every number from 3 up to n, or 3 up to n minus 1 inclusive. I only have to check all the numbers from 3 up to the square root of n to check for primes. Because if it's not a prime number, well, somewhere in that range I will stumble across one of these factors. So this is why we can start at 3, because we've handled all the even numbers before this point. I don't have to bother checking the even numbers now. I've taken care of all of the even numbers before this. Namely, if it's 2, this is a prime number. If it's an even number that's not 2, it's not a prime number. So I could start at 3, I only have to go up to the square root, and I could try all the odd numbers. I don't have to try 4 or 6 or 8, because I've taken care of those. I only have to try the odd numbers. Is there a name for this isPrime method? Well, we were just calling it isPrime fast. There are other, even, kind of slightly more sophisticated algorithms which can check for primality. Someone wrote one similar in this in one of these questions. I can't. Oh, I think it might have been this one here. Blah 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 blah. Someone did this. There's someone who wrote another function in one of these questions. I can't remember who it is. Apologies, I can't remember who wrote it and the name of the question. But there is a way we could even kind of speed things up a bit more. Namely, if we have a prime number which is larger than 5, then that prime number is equal to 6 times some number k plus 1 for some k, or is equal to 6 times k plus 5 for some k. Right, so let me make a remark, right? Remark: any prime number larger than 5 can be written in the form 6 times k plus 1 for some k, or 6 times k plus 5 for some k. In other words, a number, well, let me just say it in words, right? If a number is prime, if I look at the remainder when I divide that number by 6, I'm going to get either 1 or 5. This isn't saying that every prime number, that every number of this form is prime. That's not true. Right? But I could use this kind of information, and I could, if I'm slightly careful, I could write a kind of even faster function to check for a prime number. Yeah, we don't treat 0 and 1 as a prime number because, we'd have lots of special cases to write down. So 1 is not considered a prime number. 0's definitely not a prime number. 0 is divisible by every positive integer, say. Right? 0 divided by 10 is 0, which would kind of fit into this definition of it not being a prime. Yeah, we don't consider negative numbers as prime numbers either, because, well, right, I could write -2 as -1 times 2, for example. So yeah, we don't consider negative numbers as being prime numbers. And if you want, yeah, someone's suggesting I could say, instead of if number less than or equal to 1, I could say if this is less than or equal to 2. Sorry, less than 2, not less than or equal to. And my assert statement still holds. Now, right, return a function which will find all prime numbers up to and including n. Well, I could use my get primes fast. I could write a list comprehension. Alright, I could say number for number in range, say I start from 2, n plus 1, because 1's not a prime number, if is prime fast number, number. Get primes fast of 100. Right, 2, 3, 5, 7, 11, etc. Get primes fast of 1 gives me an empty list, which is what I want. Get primes 2, get primes fast of 2 gives me 2, yep. If I go up to 3, I get 2 and 3. If I get 4, well, I still get 2 and 3, and so on. Right, if I go up to 50, well, I get these prime numbers. So my get primes fast function is being tested here. Right, we write a function which takes a parameter. We give the name of this function to the grader. The grader runs our function on some test cases and checks if our function gives the correct result on all of those test cases. I don't remember what the test cases are, right? But this runs the function on some test cases. And if I get all the test cases correct, well, we get a score of 1. If we have some of our test cases wrong, well, we'll get a score less than 1. Collins, I think it's just a matter of taste, whether you use a number less than 2 or less than or equal to 1 right here. You'll get the same results. Maybe it's a matter of style or preference or whatever your taste is. I mean, I would tend to use less than or equal to 1 right here because, well, it's a little bit easier for my brain to parse it later on. Right here, if I put in 2 and I'm trying to reason through this, well, my brain might take a slightly longer time to parse this. Oh, if number is 2, oh, hang on, this is going to evaluate to false, and I will be down here. Whereas if I wrote less than or equal to 1, I think my brain parses that a bit quicker. But it's a matter of taste. Right, yeah, it says here there's a faster method as the Sieve of Eratosthenes to generate prime numbers. And the idea of the Sieve of Eratosthenes is as follows. It says generate a list of all the numbers between 0 and n. So what do I do? Well, let's suppose n is 12 for something definite but also something small. I can think of writing down, right, if I just follow the procedure outlined here, I'm going to write down all the numbers between 0 and 12 inclusive. Right? So generate a list of all numbers between 0 and n inclusive. Let's say we include n. Mark the numbers 0 and 1 to not to be prime. So I will mark 0 and 1 not to be prime. All right, I've done that. Starting with p equals 2, the first prime, mark all the numbers of the form n times p. Well, if p is 2, I want all the numbers of the form 2 times n, where n is strictly bigger than 1. And n times p is less than or equal to this number, capital N. Right, so what do I want to do? Well, 2 is prime. I'm going to circle the prime numbers. Now I'm going to mark out every positive multiple of 2. I mark out 4, I mark out 6, I mark out 8, I mark out 10, I mark out 12. Those numbers can't be primed. Oops, where's my IP? Find the smallest number greater than p, which is not marked. Set that equal to p, and then go back to step 2. So I look at my list. This number right here, that is the smallest number that's not marked out and is larger than 2, is 3. Now I mark out all of the multiples of 3. I could mark out the same number again. I mark out 6, I mark out 9, I mark out 12. And then I repeat this, right? Find the smallest number greater than p, which is not marked. Yep, I marked out 9. Yep, right, 3, I marked out 6, I marked out 9. I'd already marked out 9. No, I hadn't marked out 9. I marked out 6, I marked out 9, I marked out 12, because they're all positive multiples of 3. Now I look here, oh, the smallest number that's not marked out is 5. Well, I would mark out 10 again. I would go to 15, but 15 is beyond 12. Now I mark out 7. I would mark out all the multiples of 7, but there are none smaller than 12, and 11 is not marked, so that's a prime number. All right, this is the Sieve of Eratosthenes. Basically, I keep 2, I cross out all the positive multiples of 2. Then I keep 3, I cross out all the positive multiples of 3. I keep 5, I cross out all the positive multiples of 5. I keep 7, I cross out all the positive multiples of 7, etc. Right? I mark out all the multiples of a prime number, because all those positive multiples aren't prime numbers. And so this is what we want to do, right? We want to implement this Sieve of Eratosthenes. I might be saying his name somewhat correctly. Right, so I want to, generate this. We're suggesting here to do the following. Make this function called listTrue. Make a list of true values of length n plus 1, where the first 2 values are false and all of the other values are true, right? This corresponds, as we said, to step 1. So 0 and 1 are not prime numbers, so we're going to start our list with false and false corresponding to 0 and 1, and we're going to make a list of other values which are all true. So I'm going to return a list of false and false, or, well, all right, there's several ways I could do this. False and false, and I'm going to append a list of true for I in range. Well, I start at 2, and I want to go to up to and include n. List true of 5. So 0, 1, 2, 3, 4, 5. 7, 0, 1, 2, 3, 4, 5, 6, 7. There's another way I could consider making this list true of n. Return I greater than or equal to 2 for I in range of n plus 1. List true of 7. Again, I get false, false, true, 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 true. 0, 1, 2, 3, 4, 5, 6, 7. Right, so I could kind of explicitly construct 2 values being false and the remainder that I want to be true. I could get the same result by using a Boolean expression. Assert length of list true is 21. Assert this value is false. Assert these 2 values are false. Yep, the first 2 values are false. Then I want to, make a function which it says will take in a list of elements and a number p and marks false elements false, which are in the range 2p, 3p, etc. up to n. So yeah, Ulrich, that's all right, right? There's usually more than one way to skin a cat, as the saying goes. I want to make this, next function that says mark false is going to take in a list. It's going to take in a value p. I'm thinking here, well, we're using p because generally we're thinking p is a prime number, although it doesn't have to be. All right, this will work for any value p. What do I want to do? Well, I want to, I'm going to return my Boolean list after I've changed it. What do I want to do? I want to, for I in range, I'm going to start at 2p. I'm going to go up through, so I could scroll up. So here's my 2 approaches to make my list that I wanted, right? The first 2 values are false. All the other values are true. So remember indices, in terms of indices, I have 0. Oh, you can't see my cursor. That always annoys me. Right, but I have 0 and 1 are false. And then indices 2, 3, 4, 5, 6, and 7 are true. Because you want to include up to index 7. We're going to finish this mark false here tomorrow because, well, we're out of time. Right, but basically we want to, write a function which will do this kind of crossing out that we talked about here. If we gave it 2, the value p is 2, we want to mark the Boolean values on this list at indices 4 and 6 and 8 and 10, as much as possible. We want to mark all those values to be false. And we shall do that tomorrow, right? Well, I'm going to start it I could kind of give you the answer here, right? I go up to the length of the Boolean list. I go in steps of size p. I mark the element at this index to be false. Right, so I start at value 2p. I go up to and include up to the end of the length of this list. And I go in steps of p. So I'll have 2p to start with, and then 3p, and then 4p, and 5p, and so on. So, right, this parameter here says I go up in steps of size p. I mark all the values at these indices to be false. And we shall pick up here tomorrow. But as I said, bring your other questions, and we could finish up this question here and talk about your other questions that you bring tomorrow. So I shall wish you all a good day, and we'll see you tomorrow.